Imagine a 1-pound steel hammer tumbling through the vacuum of deep space. It's heading straight for Earth at 99.999% the speed of light. Under the established laws of physics, no object with mass can actually achieve exactly 100% of the speed of light. Doing so would require an infinite amount of energy. But as a thought experiment, we can look at what happens when a physical object pushes right up against that unbreakable cosmic barrier. Brushing against the ultimate speed limit of the universe rewrites the physics of a collision. The hammer's material properties vanished, replaced by raw kinetic violence. This graph maps normal kinetic energy. Speed and energy share a steady, linear relationship. But as speed approaches the speed of light, c, relativistic physics takes over. The steady climb disappears as the object gains mass, and the energy curve skyrockets vertically off the chart. Because of that exponential energy curve, the tiny mass of a hand tool now carries the destructive potential of a massive celestial body. Let's track the exact moment this hammer hits the outermost layers of Earth's atmosphere. Normally, an object falling from space pushes air out of its way, creating heat and friction. But at this speed, the oxygen and nitrogen molecules in our atmosphere cannot physically move out of the way fast enough. The hammer slams directly into those stationary atoms. The atmospheric molecules compress so violently that their nuclei fuse together, triggering spontaneous nuclear fusion and a blinding surge of intense gamma radiation. The hammer descends behind a perpetual wall of nuclear fire, compressing the very air into a continuous fusion reaction as it falls. A fraction of a millisecond later, that plasma shockwave and the pulverized remnants of the hammer strike the Earth's crust. The impact site vaporizes instantaneously. The soil, bedrock, and everything nearby convert directly into superheated gas, feeding a rapidly expanding fireball of plasma. Deep below the surface, the kinetic energy triggers seismic shockwaves, excavating a massive crater into the bedrock in a fraction of a second. This level of devastation mirrors the touchdown of a massive asteroid, proving that extreme velocity can effectively override mass. To quantify exactly how much energy is being released, we can look at historical benchmarks. This bar chart compares our theoretical strike to humanity's most destructive creations. The small bar on the left is the Tsar Bomba, the largest thermonuclear weapon ever detonated. The hammer's impact yield easily dwarfs it, delivering tens of thousands of megatons. Zooming out, we map this event against the Chicxulub asteroid strikes tectonic dinosaurs. While not triggering global extinction, it registers geologically. A single 1-pound piece of hardware possesses enough concentrated energy to collapse the local climate of an entire geographic region, which raises a question for planetary defense. Could modern radar or near-future space tech track or intercept a threat like this? This diagram illustrates a hard limit in how we monitor the sky. Telescopes rely on capturing light, but because this object is traveling at 99.999% the speed of light, the physical mass and the light are moving side by side. The visual warning arrives a microscopic fraction of a second before the physical hammer strikes the ground. Advanced warning or deflection is physically impossible. The arrival of the observational data and the arrival of the destruction are effectively simultaneous. We historically look up and fear massive, slow-moving threats. We scan the darkness for heavy comets and gigantic asteroids. But the laws of relativity show us that velocity is a far more potent and efficient weapon than sheer mass. At the absolute limits of the universe, a household tool carries the power to level a mountain range and darken the sky for a generation.